You all know the speaker, Nigel Mottram, and you can read the title, so the introduction is now complete.
Thank you.
Sorry.
No, that's fine. It doesn't need anything else. That's fine. Okay, so I'm going to talk about modelling bistable displays. In fact, in general, about modelling with the Q-tensor theory, and actually, in fact, I'm going to also talk about director models as well, and compare the two. And sometimes direct model seems to be better than Q-tensor theory, in fact. Okay, so this whole project has been long running now and came out of a PhD project at Strathclyde. I think it was about 5, 6, 7 years ago now, and we were just looking at implementing a numerical scheme for Q-tensor models, and looked at some of the simplest geometries we could just to test the code. In fact, we wanted to go from 1D to 2D, and so we started looking at the simplest geometry we could think of, and that's a square box. So it's in 2D, and we fill this with liquid crystal, and we impose some boundary conditions. In boundary conditions basically being that the director, as it were, likes to lie parallel to the edges, and we just saw what happened. And this is the numerical solution that came out of a Q-tensor theory. And I'll talk about this a lot more in future slides. But all I want to say here is that the motivation for the whole of this work came when we took different initial conditions for our numerical scheme. In one case, we got this system where the director lies diagonal across from corner to corner. And we got, effectively, I'll talk about these in a bit, but two defects, one at each of the opposite corners here. And another possibility was the director lies roughly vertical. In the bulk of that, in the majority of my square region, my director's lying vertical in this sense. There's no there's no gravity, there's no vertical, but just vertically on the board. And the two defects have moved, well, one of the defects has moved from this corner over to this corner. Okay, so there's some defect movement. So to kind of model this, we assumed you would need a Q-tensor theory which allows for defects to be modeled. Okay, so some acknowledgement before I forget. So this original project was, Gavin Kelly was the student, and it was co-supervised with Alison Ramage. She was the expert on the numerical side of things. After that, we realized we had something that might be worth patenting. So in fact we did, spurred on by some funding coming from Scottish Enterprise. And then it spawned a whole load of other projects. Lots of people got involved with different types of bistable and multi-stable devices. And I'll show you a few of those soon. And in fact, the original patent now is being exploited and commercialized by a company called ZincTech, who hopefully are going to make these displays for real. Okay, so what I'm going to do is just a little bit of recap of, and we've seen lots of these things before, but I thought it might be useful. Because I'm going to compare Q-tensor theory and director models, I thought it would be worthwhile doing a bit of background of the two of them and just explaining the models. Okay, so we all know we're thinking about a system where we have a ball of rods, and these are notionally the molecules in our liquid crystal material, and they may well, usually with a reduction in temperature, align along some average direction. And this is the director, okay? So the average orientation of our molecules defines the director. And because our molecules are headless, they don't know up or down, then the director should be the same whether it's n or minus n. They should, in our theory, be equivalent. Well, the other parameter that we might want to measure is not simply the direction, but what the spread around our average direction is. So we use essentially the probability density function of the angle, theta m, which is the angle between the molecule and the director. Okay, so this is the appropriate measure of the spread of the director distribution of the molecular distribution about the director. And S, and it's this polynomial because S then varies essentially between 0 and 1. And when we have S equal to 0, then it gives randomly oriented rods. This would be a probability density function that's just flat. Same probability of having a rod in any direction, so that's this case here. So when S is 0 in all of the slides to come, that means a randomly oriented rod grouping. And when S is not 0, in fact positive it's going to be in my case, S is not 0, we have a preferred direction. So a director can be identified, and S is non-zero as well. Okay, so that's fine. That seems to, and that's, I'm going to talk about Ericsson theory, which the model is based on those two dependent variables. But that's not the whole case. In fact, the S and N variables fail to model some situations. So if we think now, instead of our ball, we think of a squashed ball. So what I've done here is I've got my ball, but I've squashed it in the Y direction. So I'm thinking of my, however this happens, this could happen maybe if my molecular grouping there was next to a surface. Or there might be topological reasons why I get this, and I'll show you some of those in a minute. So we think about this kind of squashed group of molecules, and then if we were to view this set of molecules along the x-axis, okay, so along the x-axis, because I've squashed this, actually the order increases. Now my molecules are more aligned. There's less variation from the director, which is the vertical Z direction here. Okay, so I've increased the order by that squashing. But if I look along the y-axis instead, or I can look along both of the other axes, but let's look along the y-axis. Along the y-axis, my order parameter may not have changed at all. I've got the same amount of spread in my molecules. And so it seems that depending on where I look, along the x or the y-axis, I've got a different value for my order parameter S. Okay, so different values of the order parameter S, well, this is biaxiality. By squashing my ball here, I can now define uniquely three different axes, the x, y, and z axis. Before, in my unsquashed ball, the x and y axes were essentially the same, and I had a degenerate system. Okay, so biaxiality, how do we model biaxiality? And we've seen this before. Well, we think about actually the second moment tensor of my distribution of these molecules. So L here is my, each of my little molecules have a vector L. Okay, so in fact I don't use M, I use the traceless part of M. It's more convenient, and that's the Q-tensor. Okay, so this is our Q-tensor, and it can be decomposed into directors and order parameters if you really want. So this is an expression where I now have, you see, two order parameters. It's traceless, and so there isn't a third order parameter. And it's in terms of a director N and a director M. Okay. If I constrain the system to be uniaxial, then actually, well, I can set S2 is 0, and I'll mention that again. When I set one of these order parameters to 0, either S1 or S2, in actual fact, I get back to a uniaxial system. Okay. So, continual models of...
Let's go back to
yeah.
the previous one. You've got S1 and S2, which are scalar.
Yeah.
And you've got N and M, which are two-dimensional, because they're on a projected.
Well, M's perpendicular to N.
Okay, right.
So that's how you got... Yes, okay, I should mention that. So we've been talking, of course, about 5 variables. And here we do have 5 variables, because S1 and S2, there's 2. N has 2 variables, and M has to be perpendicular, so it's constrained, and that's 1 extra variable. So we've got 5. Okay, and in this case there we would have the 3 variables, if we just uniaxial. Okay, so let's think about what models already exist. So the original model of liquid crystals, really, of pneumatics at least, was the Francosian-Zucker model. And here we're just thinking about the director N, and we postulate some free energy, which is basically made up of things like elasticity or dielectric energy and things like that. And it's written in terms of the director and gradients of the director. So we've seen those kind of models before. Ericsson, in late 80s, early 90s, I guess, I can't remember, wrote down a model which actually included the S order parameter. So again, S here, remember, is just when it's 0, I'm isotropic. When I'm non-zero, I'm a pneumatic. And he allowed S to be spatially dependent and time dependent. So you can write down, again, the free energy in terms of the director and the order parameter and the gradients of everything as well. And then Landau-de Gennes, well, there you can write down your energies in terms of your full Q. So again, we've seen those before. So you can put other variables in there. You can the electric potential actually should be in there as a dependent variable because we should solve Maxwell's equations. if we have certainly an applied electric field, and if we want to go to dynamics, we need some hydrodynamic variables like the velocity. Okay, so what I'm going to do now is just talk about a couple of those energies and just show you the comparisons between the different energies, and we've obviously seen some of these before. So the elastic energy, everyone's seen this before, the Frank energy or the Frank-Ozeen-Zocker energy. We have three classic distortions, a kind of splaying of molecules, a twisting or a bending, and these are represented in the first three terms here. We have a splay, modeled by the divergence of n, this twisting factor here, and a bend, and also the K24, the saddle splay term, which is pure divergence, and so often, certainly in some situations, will simply disappear from the bulk and go to the surface. Well, if we go to a Ericsson description, then essentially not a huge amount has changed. All my order parameters now are effectively functions of S. So my elastic constants now are functions of S. And the extra term I have is this extra term here because I'm allowed gradients in S, and it's a kind of elasticity from that. So that's the extra term gradients in S. If I then go to Landau de Gennes, and again this expression has been written before and in a talk before, here's one example of the Landau de Gennes elastic energy. I've got three terms which are essentially quadratic in Q. Four terms because this is a chiral term. This is if I've got a chiral pneumatic, and this last term here is one of a choice of a number of cubic terms in Q. And essentially I've added this in. I don't actually use that too much in this talk, but I've added this in if I want to differentiate between K3 and K1. If I don't have that term in, then I can't tell a difference between two different elasticities of K1 and K3. Okay. So, and we can, as I say here, we can relate my L parameters, these kind of elastic parameters, to the Frank elastic constants. Well, in terms of a thermotropic energy, and the thermotropic energy really just models the preferred state. It's a function of the temperature, the preferred state that the system likes to be in. So at a high temperature, we're looking at the uppermost curve here. So this is this thermotropic energy as a function of, here I've got it as the order parameter S. And so if at high temperature, that's the upper curve here, the only minimizer, the only minimum on this curve is just the isotropic state where S is 0. As temperature reduces, what I see is a metastable or locally stable pneumatic state here, and gradually as temperature decreases, the energy of this state decreases, and it becomes essentially more stable, as it were. At a critical temperature, the stability of the isotropic and the pneumatic state are equal, in the sense that the energy is equal. And eventually, if I reduce temperature even further, then gradually my pneumatic state gets, the energy gets lower and lower, and eventually it's the only state that's stable. The isotropic state actually becomes unstable. Okay, so in an Ericsson description, this whole behavior here can be modeled, and you can see what it is here. You can model this with a quartic polynomial in S. It's relatively good model. The one problem is that if I do model this as a quartic in S, then I'm allowed, under certain conditions, S could go greater than 1. And S isn't allowed to go greater than 1 on physical grounds. That's how we defined S. It can't be greater than 1. So there are problems. Now, if you force the system hard enough, if you have a very high electric field, you can get S greater than 1. And you can push the system up here to very high energies in terms of the thermotropic energy to S bigger than 1. In a Landau de Gennes, I'll explain the diagrams in a minute, in the Landau de Gennes approach, it's a similar function here. Now we're essentially a function of trace q squared and trace q cubed. Trace q to the power 4 is obviously related to trace q squared all squared, but I've just written it like this. And what I've got here is it's a little hard to draw this function, but what I've done is I've fixed the eigenframe of q. So q here has an eigenframe along the x, y, and z axes, for instance, and I'm just looking at my potential energy, this thermotropic energy, as a function of the two eigenvalues, or equivalently the two order parameters. And as I reduce temperature, I see three possibilities, three minima. Each of these are stable, they're pneumatic states, and essentially the difference in the three is simply I can have a pneumatic aligned along the x-axis or the y-axis or the z-axis. Okay.
Can I just ask
Yeah.
a question? So if you put the uniaxial ansatz with s depending on x into lambda de
Yeah.
does that give you exactly the form you gave for the Ericsson theory? Because I had the impression that there were some terms that were slightly different or something, or that he'd added or something, but I've forgotten. It's a long time since I did the
I think the parameters might rescale, but I don't think there's
There's not.
any other terms.
There's not one, no.
I guess these are just
No, I'm not
Polynomials
worried
in
about
the-
those terms. Well, also the,
when I
the elastic terms, for example.
oh in the elastic terms okay in the elastic terms
So if you just shove in the ansatz, q equals s of x, a times n minus the identity into that.
With kappa 1 becomes 1/3.
for the Ericsson.
For the Ericsson.
For the Ericsson, okay, yeah. For the Ericsson, if I put in, yeah. Just as there's I can't go from lambda de Gennes to Frank energy, the full, so K3, if I go from lambda de Gennes to Frank energy, then I get an expression where K1 and K3 become equal, they are equal.
Not if you use L6.
Oh, if you use L6, yeah. So if I go from lambda de Gennes to Ericsson, then something similar happens. In that I can't get the full, so the kappa parameter there actually, it's a function of L1, I guess. I think it's a function of one of these parameters. So I can't get the full, the full Ericsson energy out because the parameters in front of each term are dependent on each other. Okay, so boundary conditions are quite important, and I'll show you about that in a minute. So often, sometimes we use simple Dirichlet conditions, so we fix, this is called strong anchoring or infinite anchoring really, and this is where we fix either the director, the order parameter S, or in total the Q-tensor at a boundary. We can do weak anchoring, and weak anchoring really just says there's a preferred direction or state on that surface, but we can vary away from that state, but it will cause an increase in energy. So there's different forms of that energy. In a director-only model, the classic form of that surface energy is this. This is, some anchoring constant W, and then a function here which is minimized when n equals the preferred direction n0. And the equivalent in Q-tensor, we can just write down something very similar in that this here is minimized when Q equals Q0. Okay, so there's a preferred direction, and if I go away from that preferred direction, my energy increases. In fact, what the energy I'm going to use is what's called planar degenerate. So here, the surface, we imagine, only likes simply that the director, or actually an eigenvector of the Q-tensor, to lie parallel to that surface. You can lie anywhere on that surface, but it's got to be parallel. Well, it likes to be parallel. And this is an energy which basically models that. There are two parts to this, really. The first three terms there really are understand where the surface normal is, nu, and they really are setting, effectively, they're setting the eigenvectors of Q to be with one of them along in the plane of the substrate. The last three terms here, well, these three terms here don't adequately set the order parameter, the eigenvalues of Q. And so these last three terms here we use to actually model a preference for the eigenvalues of Q on that surface. The surface would like to induce some form of order, whatever that order is. And these three terms allow you to then tune that slightly. In fact, we actually set the surface preferring to have an order parameter or an eigenvalue the same as the bulk. Okay, so a simple example. I'll just run through a very simple example and then go on to some more complicated things. It seems a simple example, though it's not as simple as first we might think. So here we have two surfaces, two substrates, the top and the bottom there, so they're infinite in extent, and we just have a one-dimensional system where we've got pneumatic liquid crystal sandwiched between these two substrates. Usually these are glass or plastic in an experiment. And I'm going to assume they're a distance d apart. I've set up some axes here, and the director on the bottom substrate I've fixed to be parallel to the x-axis. I've then fixed the top director to be at an angle alpha to that top, to the surface, and I've got infinite anchoring or strong anchoring at the substrates. But what I'm going to do is actually, so actually when alpha is non-zero, I set up some elastic distortion in the liquid crystal, and the elastic energy is non-zero. And what I'm going to do is I'm going to gradually increase this angle alpha. Okay, so I get more and more elastic energy as alpha increases. Okay, so if I just model this with a Franco-Ziethe-Zocker model, so a simple elastic-only model, then my director I can write simply in a one-dimensional system. It's just a function of z as the angle from the x-axis to the director. Okay, so theta is this angle. And then I can work out the solution. The solution actually is just, well, in a one-constant approximation, and this is, I've just used a one-constant approximation, is always going to be a linear function of z. So my theta, this is theta on the vertical axis, and it varies linearly from the bottom substrate to the top substrate. And as my angle alpha at that top substrate increases, I get more and more elastic distortion. And you can see my energy here just increases, and it increases quadratically with alpha. Okay, so that's all very well known, that's fine. It will keep going on forever. And this is because of a couple of things, because of the fact that I'm using a director-only model, and also because I've got strong anchoring. If I go to an Ericsson model for very thin layers, then what happens is this. For small director angles, as I slowly kind of increase the elastic energy, I do get this quadratic behavior of the elastic energy as a function of theta. But gradually, what happens is I get this rather sharp distortion in the middle of the cell as I crank up the elastic energy. And what's happening here, in fact, is that I'm going to get localized melting of my liquid crystal right at the center of the cell. And this is the highest energy here. This is just before the highest energy when I'd get an infinite gradient in theta. I'm allowed an infinite gradient in theta because at that point, this is my S order parameter now, as I change the angle alpha, as I make it more and more elastic distortion, what I get is S going to 0. And so I start from something nice and simple with a constant order parameter, but eventually I get to this system where I get an infinite gradient in my director, but because my order parameter is 0, then the actual total energy is bounded. So the lowest, for lowest elastic energy, S is constant. For high elastic energy, this localized melting occurs.
Sorry, Nigel.
Yeah.
Does it occur for all values kappa 1?
Well, I think depending on well, it depends if you scale out the gap width. It depends on this. I'll show you another. It doesn't depend on all values of kappa 1, but I can always make it like this for any value of kappa 1 if I have a thin enough layer. Yeah. So I could rescale out. If I non-dimensionalized, actually it's kappa over d squared, the distance squared. If I have if I have a thicker layer or a smaller value of kappa, I guess, then something slightly different occurs. Oh, sorry, one other thing. What happens as I increase alpha, so if I'm increasing the angle here, I get to pi over 2, I get this melting occurring, and then essentially I get reformation of my standard pneumatic structure, and no melting at all, because I've changed the orientation. This rotates clockwise, and this one rotates anti-clockwise. So I kind of reform with a reverse splay. For a thicker layer, so now my distance here is thicker, I'm actually allowed to have more elastic energy, and as I increase my elastic energy, I'm allowed to have more distortion. As I increase, my distortion goes past this, what was a critical value of director angle pi over 2, and I'm allowed to go past and have this amount of distortion, but eventually this branch of solutions here loses stability. There's a fold bifurcation here, and in fact, if I were to increase the angle, I would drop off onto this. This is the reversed splay branch. Okay, so these thick layers can go past this angle pi over 2 before losing stability, and then this transition is dynamic. Okay, so I need a dynamic model to actually model the transition from this branch to this branch as they fall off. And there's a set of unstable solutions here as well. Okay, so a Q-tensor. Now, Q-tensor, what happens with a Q-tensor? Well, one thing just to note quickly is that, remember the uniaxial state, the preferred state of my liquid crystal, can occur when either S2 is 0, I'll have a uniaxial state, or in fact S1 is 0. Okay, so both of those are possible. What actually happens in the Q-tensor is very similar to the Ericsson model. This is exactly the same diagram for thin layers. I get exactly the same behavior, and it's simply the behavior at this melting point that actually changes. So here instead, this is the diagram I had before, just turned around. Now it's a little bit easier, because now this distance through the cell is along this direction here. At one substrate, at this substrate here, I have my director lying along this horizontal direction. I've got my order parameter here being, well, it's rescaled to 1. And at the other surface, as I go along, what I get is an exchange of eigenvalues to a different director orientation. And so what I have is I start out with essentially S2 is 0, as one uniaxial state, and I go to S1 is 0 with the other uniaxial state. The director doesn't change. In fact, the directors, the eigenframe, is the same all the way through the cell. And it's simply the eigenvalues that are changing. And in this region here, I get biaxiality. It's biaxial because all 3 of the eigenvalues are not the same.
Nigel, right in the center, it's uniaxial.
Sorry, yeah, okay, so that's that point there. Right at the center, you can see 2 of the eigenvalues are the same, and in fact, that is a uniaxial state. It's an oblate spheroid, as it were, rather than a prolate spheroid. Yeah.
So, can I ask my question again, because I'm still a bit confused?
Yeah.
There's a term in the Ericsson model which is something like S times the gradient of S squared, am I right? Or
That kind of thing, yeah.
now that can't come from the Q-tensor, can it? Because if you put the uniaxial ansatz into the Q-tensor, in order to get 2 S derivatives, you'd have had to put the gradient twice on the S, but then it wouldn't be multiplied by S, right? I mean, there are quadratic. The terms in the Q-tensor are quadratic in the gradient of Q, right?
Yeah.
So if you're going to try and get the Ericsson model from the Landau-Dijon one, then in order to get gradient S squared, you would have had to differentiate the S twice, but then it's not multiplied by an S. So I'm wondering how that relates to this kind of issue here.
Yeah. Well, the Landau-Dijon does have gradients in S alone. It's whether there's a prefactor of S is the question, I think.
Why does it have...
Is it your L6 term that should
I
generate
think
something?
that's right.
The L6 won't do it because that's only got one gradient on Q. No, it's got 2
No, it's got
gradients.
2.
Oh, that's the one. So that
I think
maybe
that's the one that comes in.
So you're absolutely right. Yes. Okay. Maybe it's that that gives it. Yeah. Okay.
Yeah, okay.
So that will give you. You're right. Yeah, absolutely.
So it's Q, gradient, Q, gradient.
Yeah, that's where it'll come.
Okay, so one other example, an important example in fact for later, is that if I allow weak anchoring in any of these models in fact, then actually I can get away without melting at all, without any, well, essentially the eigenvalue stay almost at their equilibrium value, and it just involves directed changes. And the reason, well, this depends on how weak my anchoring is, of course, but if my anchoring is weak enough, then I have a very similar diagram actually. As I change the director angle, my energy increases, but in falling off this branch, I don't transit to this reverse splay branch here through melting. I transit through a breaking of the anchoring at the top. And so you can see I can go from one orientation, clockwise to anti-clockwise, or the other way around, just by breaking the anchoring at the top. And those are the 2 states I show here. Okay, so it is similar behavior. I don't have any melting there, and in fact I don't need any defects, as it were. The melting is like a planar defect. I don't need any defects within my region. Okay, so in summary, well, director model is actually pretty unphysical as long as I have Dirichlet conditions. If I don't have Dirichlet conditions and I have a weak anchoring, then it's not too bad. It can be okay. Ericsson model and the Landau-Dijon do in fact permit melting, so that's great. If you want to see what that does, it's an exchange of eigenvalues effectively rather than a change in eigenvectors of the Q-tensor. And weak anchoring, as I said, doesn't need melting at all. Okay, so what happens in 2 dimensions? Well, let's look at a two-dimensional liquid crystal, and here is just, see in this kind of picture before, it's the Schlieren texture, and here at all these points here there are defects of some form, well, disclinations at least, not necessarily defects. Here there definitely is a disclination line and certainly a defect, and where the director really is not defined. So one of these, this is a half defect, whether it's a plus or a minus half, it's hard to tell, but it's one of these at least. And so here we have a director structure in 2D where I have a singularity effectively in the director. It doesn't have to be a singularity in the Q-tensor, but if I'm using a director or model, then it will be a singularity. Okay, so this defect here is a plus half defect, and if we transit across this defect, if we move across from A to B, what do we see? Well, we see something that's very similar to what we saw before. We go from horizontal orientation to vertical orientation, and in fact, we see exactly the same type of eigenvalue exchange as we go from one side. So this is the exact, just a reproduction of the previous picture. As we go from A to B, we see exactly the same. So this is Tim Slukin's work from a long time ago, showed this kind of biaxial core in the defect. And if we look at this, if you remember my thermotropic energy had these three different minima if I fix my eigenframe, and as I go along this A to B, my eigenframe is actually fixed. Then what I'm doing is I'm essentially journeying from point A in this minimum to point B in this minimum. And the key thing is the shortest distance across this mount impasse does not go through the 0 point, the S equals 0 point. So I don't have to go through a isotropic state. I can go across this biaxial hump here. So it's biaxial along this, certainly along this, this spur. Okay, so let's get to bistable displays. So bistable displays, lots of people are interested in bistable displays, mainly because they can maintain a static image. So if I've got black and white pixels, and both the black pixel and the white pixel are stable intrinsically without any applied voltage or anything, then I can maintain an image without power. So these are 4 examples of bistable displays. All the 3 of these, so this Fujitsu one, this Hitachi, and the Kent State one, the Kent displays, are all really demonstrators and aren't really for sale. The Kent, this is a demonstrator. The Kent do sell bistable displays. They're a bit simpler than this tablet here. This Zebedee display came out of the MOD, in fact, in the UK, and is now actually being sold as shelf labels. And the idea with this is that it takes no power to actually show you what is happening, what the price of the Coke is, but you might want to change the price of the Coke centrally, and you can do that. You just give it a pulse of power, it displays a new image, and that's your new image, new price of Coke, or whatever's on the shelf at the time. Okay, so the first thing we looked at when during this PhD was this simple box, and we didn't realize we were going to find a bistable display, but we did eventually. So what we have is we were doing Q-tensor theory. We have planar degenerate boundary conditions. So my director actually doesn't have to line the plane here. I have a layer of liquid crystal, but I allow my director to come out of the plane. It just likes to lie parallel to this. This is a vertical wall, as it were, and this is another vertical wall. They can come out of plane. If I throw my liquid crystal into there and give it some initial conditions in the numerical scheme, then I get this system here. So here's my little directors, and here's the kind of the bulk orientation of my cell, and this is really what we would see optically if we were to form a display out of this. We'd see basically the directors all lying along a diagonal. So this is the eigenvectors of Q. You can see there's some high distortion in each of the corners. And this high distortion, you can kind of see it's a bit of a rough plot here, but these are the eigenvalue, well, one of the eigenvalues of Q. In fact, it's 2 times the order parameter over 3, 2/3 of the order parameter. And you can see here there's a reduction in order at these corners. Okay, so it looks like we've got something that might be defect-like at the corners. In fact, what we did was we smoothed off the corners, because actually this was a part experimental project and no one can make very sharp corners in experiments, so the experimentalists didn't like it when we showed them these pictures of very square wells. we actually made the corners a little bit curved, and what we see is that actually these regions on these corners aren't defects at all. You can have a continuous deformation of the director as we go around, but we do need defects in these other two corners. Okay, so and gradually as we smooth off these corners, we round them, we change the curvature, the defect comes in a little bit, but then actually it doesn't come in very much, it just sits at this boundary. What we can do also is we can, one thing, just these defects here are just half defects. You can tell topologically that we must have defects that sum up to 1 in this system. We've got essentially homeotropic anchoring here in this case. We can have planar or homeotropic. We've got homeotropic anchoring in this case, because of that, we need to have all the defects in this region adding up to 1. So we've got 2 halves. Okay, so we can apply a field. Now, when we apply an electric field, we can reorient the bulk of our liquid crystal. All these directors just swing round, and they swing round into the direction of the field. So if we put the field in this direction, then we can switch from this state to this state. We still have these 4 high distortion regions in this square. But critically, both states are stable. And here we suddenly realized that there was a bistability here, if we could manufacture this. And we can do lots of things. So here I've applied a voltage, and here's the elastic energy measured against time after I apply a voltage. What I see is, as I switch from one state to the other, I see a different energy barrier. And the energy barrier really is dependent on how rounded the corners are. If I'm completely, this isn't a circle, it has got flat bits to it. If it's a circle, an actual circle, then there's no energy barrier. I can just continuously move my director around to the other orientation. But whenever there is some corner, even if it is a rounded corner, there's an energy barrier to get across. And this is a fairly rough plot, but what this is I've changed the field angle from 45 degrees to minus 45 degrees, so I'm effectively switching from one state to the other for a load of different types of from square round to very rounded off square. And what I see is that essentially the energy barrier, this is the elastic energy, the energy barrier again reduces as I round off the corners. There's some other interest here. These minima here are actually because of the electric field. The electric field actually causes these minima when I'm not aligned along the diagonals. And the other interesting thing is I also found a minimum at 0 field angle. Okay, so that's not at diagonals, but it's where the director is roughly parallel to one of the sides. Yeah.
Where is that energy density measured? In what part of the cell?
That's integrated over the whole cell. Oh, sorry, did it say density? Sorry, I should have said energy. It's not an energy density, it's integrated over the whole cell. Okay, so actually I find 3 different states. I've shown you this one here, and obviously by symmetry this one is also exactly the same, but there's another one. And this one here we have where the defects aren't on opposite corners, they're at adjacent corners. Okay, so the one thing I was interested in also is that, in fact, in a director-only model, in just looking at the Frank energy, in a one constant approximation, the equation I actually have to solve is just Laplace's equation. Okay, so here I have a system where my director angle is this phi, and so we can use conformal mapping to actually solve this problem, with some singularities added in certain corners. Okay, so, well, I'll just actually do a slightly simpler problem first. So here we have a system where we have just liquid crystal in this wedge. Okay, so I've got liquid crystal in a wedge, I've got a certain orientation on each of these surfaces, and beta 1 here is the angle, the wedge angle. Okay, in actual fact, so I can just relatively standard conformal map to actually solve Laplace's equation in this region, and here's the solution. Okay, so it depends on beta 1, and beta 2 just depends on beta 1 as well. It's just notation for simplicity here, and it depends on the 2 orientations at either one of the substrates. So I can get different solutions. I can get this kind of solution where I've got effectively lots of bend and I can get this type of solution where I've got a lot of splay. And I can analytically work out the elastic energy, and it depends on a couple of things. It depends on the wedge angle, which we would expect, and it depends on the region size. I have to do the integration here up to some region up here, some R, some radius, and it depends on the defect core size. I also have to cut out a little bit of the core here to do this integration. Okay, so I've got this analytically. I can plot the energy now as a function of the apex angle, so I can open up this angle for different types of distortion. These ends just depend on how much I rotate from one side to the other. And I can see that the lowest energy actually is either this splay or this bend, and it really just depends on how big the apex angle is, and it cuts off here at pi over 2. So the change here is at pi over 2. Okay, so we can get that kind of thing. We can also do the square box, which is a little bit more difficult because you have to use the Schwarz-Christoffel transformation to do this with conformal maps. But effectively all I do is I solve Laplace's equation, and I can write down the solution, at least implicitly, just by defining what my director angle is at each of the surfaces. And all I do is, to go from one to the other, I just change what my definition of the director angle is. It's either 0 or pi. And that just goes from one to the other. We can also investigate the transition. So we did this using Q-tensor and the switch between one to the other. What actually happened was this defect here essentially slid along this surface. And it slides along this surface. It comes out a little bit, but it's essentially, for large enough box size, it slides along this surface and transits to B. And so we can do this, again, just using conformal maps. We can now define a state where my defect is somewhere in the middle of this A to B, and I can gradually move it along and eventually find my other state. And for each of those, I can work out an energy, and I work out some rescaled energy as a function of the defect location from A to B. I see there's low energy at both of the edges. It's slightly different at each edge because there's slightly more distortion in this configuration, slightly less distortion in this configuration to this one. And so I see a slight change in the energy from going from A to B. But there's a great big energy barrier in between. And this is the energy barrier we now have to try and get over if we're going to switch from one to the other. Okay. Yeah. For this conformal map, I'm just solving Laplace's equation. So physically, I put an electric field on.
And so when you're moving it here, you're changing the constant?
Changing the boundary conditions, that's all it is. Yeah. So it's definitely and there isn't an electric field on, so it's not exactly the right director structure, but it's pretty close, actually. Okay, so lots of experiments were done. So here's some, this is an experimental, just under the microscope, we can see between cross-polarizers, we can see two different states. There's this state, and there's a kind of symmetric one just rotated. It's basically this state, but the polarizers aren't correctly crossed. And this state, so the two states, these are my theoretical pictures. I can simulate the transmission through my director structures relatively easily, and I get states that are pretty much the same. So I'm fairly happy with that. We also went on to do much more complicated. We don't just do squares, we can do hexagons, we can do any shape at all. There are many possible states now. Effectively, my defects, rather than just having two choices, either opposite corners or adjacent corners, I can now have them in lots of different corners. And in fact, if you look experimentally, we do this in channels, so it's easier to fill the pneumatic liquid crystal here in these channels, and we get a whole load of different solutions. We can identify the ones we found theoretically. This one is this one, and the vertical one is this state here. But to be honest, there's an awful lot of different states. So categorizing these would be very useful. So there's lots of that are same, and there's a lot of crosstalk, as it were, between different hexagons. But there's a rather rich structure here. Okay, so one other thing before I finish is one bistable display that's actually being sold is this Zebedee display, ZBD. Now how this works is, instead of having my two substrates planar, top and bottom, the bottom substrate is a sawtooth. And what this does is that effectively, you can imagine, so we've done some work on this, imagine my liquid crystal in this wedge here. So I've already showed you some solutions of liquid crystals in wedge. wedges, and I can either splay or bend in here. And it's that bistability actually that creates this whole bistable display. And so we can do some director modeling. We get these two different states where we either have splay in this wedge or we have bend in the wedge. So that's nice to see. This is our model transmission, and here's some experiments, rather rough experiments, but you can see that they're matching fairly well. Okay, so in summary, what I really wanted to say here is that we do use Q-tensors to model bistable displays, and they are very good, and we get some qualitative features out of Q-tensor models, but to be honest, we also use director models very successfully here as well. They also give insight, they give analytic solutions, and we can get analytic energy approximations, energy estimates really, for these different states. And in fact, Q-tensor modeling, the main problem with Q-tensor modeling is the fact that it's very intensive in terms of computational power. That's because we've got very small defects in a very large region. And our main reason for doing the director modeling, in fact, was to provide some very good initial solutions to our dynamic Q-tensor model. I haven't talked about dynamics at all, but I think in the next workshop I will talk about dynamics of Q-tensor. Okay, thanks.
Are you going to get rich?
Unfortunately not. I think we've sold all our rights to,
Oh,
we sold the patent basically. So
oh, big mistake.
So all these bistable displays seem to depend in some way or another on defects. Now, an example where, I mean, which is probably not realizable, where you could do a bistability without defects would be if you took a square and you could impose 45-degree conical boundary conditions. Then you could have one homogeneous state going this way and one homogeneous state going at 45 degrees, and it would match the 45-degree boundary conditions on each side of the square. Now, I mean, when I've asked people about this, Chris Newton, for example, he says that you can't reliably produce a 45-degree angle. But I wonder whether there was any way in which one could sort of formulate some sort of mathematical problem which would not use boundary conditions like that, but ones we usually use, homeotropic, and which would somehow prove that you couldn't have bistability without introducing defects.
well, I mean, the Kent display doesn't have defects and it's bistable. That uses a different method. That's because it uses a chiral nematic.
Oh, so it's a chiral. Okay.
In that example, those two states are effectively topologically different, I think, are they not? They have to be, I think, to be both stable. In that you, how do I get from one to the, so bistability is great, but I've got to be able to switch from one to the other. And I think to switch, if I understand that example, you have to do something. You either have to create defects and then they disappear, that's one possibility, or you have to break an anchoring.
It depends on, I mean, of course, you can always break topology if you have weak anchoring, right? Because weak anchoring.
Yeah, exactly. So you could break the anchoring. Yeah.
But I mean, okay.
The other way, and this is how some bistable displays work, is if you came out of the plane, and actually there's a invariance to rotation like this, and actually you can come out, create some twist, and come back with some twist, and actually that's the pi cell, effectively. And there's two stable states which come, don't have defects in, and essentially come out and use the degeneracy of my director to actually form them. Defects aren't too bad. I mean, it's not necessarily, Zebedee doesn't care about its defects, he likes its defects. They create stable states.
You didn't go too much into the numerics of the Q-tensor model particularly, but you did say at the end it's expensive. I mean, can't you implement it on an irregular grid or even have an adaptive grid?
So, yeah, we do. So we have to model those the defects, especially when they move.
Right.
Yeah. So, we haven't got an adaptive grid. Well, Chris Newton now at Hewlett Packard has got a three-dimensional Q-tensor model with adaptive grids, and that's great. It still takes a long time, to be honest. It's long for me. Not long for you, probably. You're used to months of a simulation. I want it to happen within an hour, to be honest. And to be honest, Hewlett-Packard got involved because they had these displays. They want to model them and optimize their display using some simulation. Now the guy down at Hewlett-Packard can make this device in a day, and then make a different device in a day, run some experiments, find out its properties. You've got to be able to beat that. So that was our aim. So 3D simulations finishing within a day is still tricky with adaptive meshing and everything.
So you're trying to find devices which will go from one of the states to the other, but at the minimal energy cost. Is that?
Yeah. There's a balance, because if your energy barrier is low, then you don't want it
It's not too stable. Yeah.
Yeah, it's not very stable. But you want to be able to get across that energy barrier when you apply a field. So that's the optimization. Really working out the geometry which gives you the best performance. The other thing to think of is that these two states have got to be optically distinct.
Yes.
You can't both look black. So that's no use to anyone. So that's the other possibility. So sometimes you play with a bit of the contrast, black to white, with the fact that it's a good switching device.
I mean, it goes without saying that symmetry is playing a key role here, because that's giving you the different but equivalent states.
Yep. So, I mean, the number of different states is useful, and John's done some work on this about the number of different states and the energy bounds as well. What would be really nice is understanding exactly the barrier, the energy barrier between two states, and when I've got bistable, when I've got multi-stable states are even better because I can get grayscale. I don't just have white and black, I have grey in the middle. So I really like them, but I also want little energy barriers between each of those as well. And I want to know estimate the actual energy barrier. So all of that needs to be done.
You didn't care much about switching times in your presentation. Usually when there's this kind of belief that the presence of defects in the texture would slow down the switching time.
Yeah, and it's true that they are slow. Now, classically,
What's the range? What's the range?
Milliseconds. So many milliseconds. So that's many milliseconds.
So this would not be useful for TV.
Well, no, but no one's. So the thing about displays is that you might like bistable displays. Why do you want a bistable display? It's because you want a static image. And so you don't want a TV. I mean, that's not a TV. A TV has got dynamic. So you never try and make a bistable display show video. Well, you can try, but it's always going to be bad. But normal TVs are monostable, and the fact is you push it out into an unstable situation, and that you can do that quickly with enough field, and then when you turn off the field, it goes back to that monostable state quickly. And so they want fast, and that's so to go to a bistable, you're always going to have a problem with video, with switching times. So the thing we have to beat in switching times for a bistable display are things like the Kindle. So if you have a Kindle and you see what the refresh rate of that is, well, the refresh rate of a Kindle has to be smaller than the time it takes you to read a page. I mean, really, it's got to be maybe a second, or maybe it can't be too slow, but it's got to be. It doesn't have to be video rate. So that's not too bad. If we have to refresh within a second, that's not too stringent a condition.
In your anchoring energy for the Q-tensor, you had 6 terms in there, but probably 5 would suffice, right? You only have 5 independent constants. You could imagine expanding a basis, Q in a orthogonal basis of 5 tensors or something.
Yeah, probably. In fact, the 3 terms which fix the eigenvector are probably a bit of overkill anyway. We've done it without 3.
The other thing I wanted to mention is that Yokoyama did this really interesting work at one point where he photo patterned the surface on a very small length scale, and he formed from the normal of the substrate a second rank tensor, just made a dyad from the surface normal.
Oh yeah.
And it turns out that couples to Q kind of in the simplest possible way. And so that seems like an interesting, effective way of getting a kind of a surface anchoring that you can control easily.
So would that allow you to have a bistable surface?
Well, he then made all sorts of patterns with this, and including ones that were bistable. But it was just a kind of an interesting idea that, that something as simple as the normal of the surface, make a dyad, average it, and then interact with the Q-tensor kind of the way that you might.
Okay.
So is that the same? Because I was asking Oleg about this, and he was mentioning a situation where you put a square grid with half sort of grooves in one direction and half sort of in alternate squares. You would have one with grooves in one direction, and the next one would be in a perpendicular direction, and then you would get somehow the director lining up either in one direction or the other direction if you did the right sort of thing. Is that the same?
Well, it's probably related. I mean, he's done different scenarios. In some cases, the photo patterning just has to do with the preferential direction in the substrate. In other cases, it's a surface relief thing. I don't know which one.
I think that harks back to what Berryman first thought about that, having not just grooves which align your director, but then two different sets of grooves and forming two different. Yeah, the people have tried to create that, and I think they have found it's bistable. You can either do it in patches, or you can have a sin X, sin Y type of surface, I guess, and that would form the same kind of thing.
Yeah, in your pictures of the different patterns, what was the mechanism that was driving those different patterns? What were you changing as you go from one to another?
Well, not much. For the two stable states in the square well, for instance, they're both minimizers of the energy. I don't have to change an awful lot. I mean, I guess if I numerically solve, I'd change the initial condition. But in terms of the solution to my energy minimization, my Lagrange equations, I haven't changed any parameters.
Didn't you say you changed the orientation at the boundary, the Dirichlet conditions?
Well, yeah, in a way.
You had to push them to
I changed the angle, but that doesn't change the director. The angle goes from 0 to pi.
Yeah.
Remember, n is minus n. So
Yeah.
physically, I've not
I
changed
understand.
anything, but mathematically, I have.
Yeah.
Yes.
Yeah.
But for the more complicated ones where you had squares and you had hexagonal patterns, those kinds of things, that's what I was thinking.
Mathematically, I would change the boundary conditions from 0 to pi, which doesn't physically change the director, but it changes the mathematics. Physically, how I get those different, well, numerically, I start with different initial conditions. Physically, in the experiment, how I change from one to the other is I have to force the system, like using an electric field, for instance. So I would experimentally.
Basically, you would use an electric field to get those different kinds of hexagonal or other patterns.
It's interesting, we've done a lot of work on if you just fill it with liquid crystal in the isotropic phase and then drop the temperature and let it just form whatever it wants to form, then you get these different states in exactly the proportion corresponding to the energy of each of those states. So inversely proportional, obviously. So it's a really nice, neat way of checking your estimated theoretical energy of each state versus the probability of seeing them when you look down a microscope. And so there's a correspondence there.
Can I go from one state to another mechanically? I can stretch the cell in some way? Or?
Well, yeah, you can. So we've done some work on taking the squares and making them rectangles. And there you, from one state, you can actually, if you were to stretch this, I guess, then, you could do that. You can go from one state to the other by changing the geometry. So just as I had my wedge, and if I changed the angle there, I would change the energy minimizer. How I get there through whatever mechanism is a different matter. But I would change the energy minimizer.
But if I could sort of do that and then go back again, could I come back reliably to the other state?
Well, no, they're bistable. So they've both got the same. Well, it depends. If I go to a region where only one of them is stable, to a region where the other one is stable, and back, then you should. Well, the other one loses stability. Now,
Well, it falls off the saddle node.
Yeah,
It
exactly.
fall off the saddle node, get on the other branch, and then come back.
Yeah, you
Like
do that.
And then sort of find the other saddle node.
Yep. exactly, yeah.
So do people do this at all?
Yeah, absolutely. That's how bistable displays work, effectively.
You do this mechanically, not electrically.
Sorry, not mechanically. Well, what do they do? I can't think of a system that does it mechanically.
It's not clear how the KDI device works. There you are writing on a flexible surface, and there's flow underneath it. The polymer network is deforming, so it's somewhat mechanical.
Yeah.
So is a type of dispersed device that you're talking about? You have a polymer network and the liquid crystal immersed in it. Is that how it works?
Mm-hmm.
And then you mechanically deform the underground network.
Right.
Okay.
There's a so-called boogie board, which is selling amazingly well. It's a cholesteric in a polymer network, and you just write on it with a style.
I guess you're changing the structure really through flow, I guess, is it? Or really through flow, because you induce a flow and the flow changes the carbon structure.
Yeah, and you're changing the polymer network. You're deforming the polymer network as well. Right. So I think you have a combination of both.
There is no flexoelectricity involved at all? Could this be done with some kind of flexoelectric effect?
Sorry, is it mine?
Could this be done with some kind using flexoelectric effect, if there is any? Has this been tried?
It could be there, but I don't think that they believe it's playing a big role.
In fact, some of these devices, so the Zebedee device, it's very interesting how exactly that switches. You could switch it using flexoelectricity, I guess, if you've got a liquid crystal that had high enough flexoelectricity, flexoelectric constant. It also could be switched just using ions, essentially in the liquid crystal.
How does this work?
Well, it's a bit tricky. So there are always ions in liquid crystals, and you move them around if you apply an electric field. And it might be that the ions are causing an internal electric field that then can actually switch your device. So there's that internal electric.
Ions.
Yes. Yeah.
So in a way that you would be putting some. I mean, you would.
So I don't know whether Zebedee put ions in. I have no idea. I'm sure the chemists would be horrified with the impure chemicals that they use. But I just don't know.
So just the impurities could cause that.
In a Coke display, do you have like an electric pattern on the back? Is that how it switches? Or do you make a voltage change that?
Yeah, so all of these displays will have some kind of matrix on the back. On the front and back, or on the back, yeah. That essentially can apply a voltage to each different pixel independently. Basically.
For your square cavities, don't you need a field that is in the plane of the device?
You do.
Okay.
So you have to use in-plane fields, so interdigitated electrodes for that. For each pixel, well, you can use, because it's bistable, you use passive matrix, passive scheme. So you can actually just put it along columns and rows, and then each pixel then you can pick out relatively easily.
And look, when you showed this picture, it looked like there were also hidden textures between the pixels.
Yeah.
So you've got liquid crystal also.
Well, that was a device which wasn't capped correctly, actually. So there's these wells, and then there's a little bit of liquid crystal just above them. So yeah, the capping hadn't been done properly there. It just showed the states nicely. That was all.
Would it be completely ridiculous to think that one might be able to get bistability in the boundary conditions somehow, some way in which you could do this?
Yeah. So people have looked at this. So you can imagine the one way of doing this is maybe making your boundary out of a material which has two orientations. So maybe it's ferroelectric, maybe. So you could switch between two different states, just actively control that boundary. Yeah, I guess. I don't know whether anyone's actually using that method yet. Not sure. But yeah, you could think of that.
Well, thank you very much.
Thank you.